So when we look at those products, we're just adding our hydrogen and our bromine. We can imply the hydrogen, so we can just put the bromine on. Do we need wedges and dashes? No, because why? So question 1, I completely agree. There is no chiral atom. Question 2.
Would it be identical returned?
That is a chiral atom. Technically, there are 2 products in question 2. Question 5, our answer in question 5, what are we adding? OH. We'll come back to that one. Do we need to worry about chirality on that one? Nope, no chiral center. Question 3. What's challenging in question 3? Okay. We have a benzene ring with a whole bunch of double bonds, and we have something next to it with just a double bond. So now the question becomes, is which of those double bonds reacts? Okay, the non-benzene ring one. Okay. Remember, one of the reasons why our benzene ring is so unreactive is because of resonance. We can shift those double bonds to each of those positions and not generate a new charge. Okay, which means super stable. So those double bonds will not react. We're looking at the exterior reacting. Now the question becomes is where should we put the hydrogen, where should we put the chlorine? Okay, your hydrogen is going to go to the position that that can't stabilize our carbocation. We could try and run the most hydrogen option, and then unfortunately we'd be like, oh, that kind of sucks because they both have the same number of hydrogens. Okay, so it comes down again to the energy of your intermediates, the carbocation that's formed. Would we rather have our positive charge at the top carbon or the bottom carbon? We want it at the top because resonance. Resonance stabilization. Remember how we said at the beginning of the semester your answer to everything is resonance? Here it is. Okay, or electronegativity. So our answer comes out, sometimes you'll see that drawn as a circle, and we would put our chlorine here. Okay. What's the extra complication on that? Stereochemistry. We do have a stereo center plus our enantiomer.
I thought you said we didn't need to show wedges, dashes if it's not shown in the reagents.
No, I did not say that. Okay. If you generate a chiral atom, you need to specify wedges and dashes. Your addition reactions will never show wedges and dashes because they're not chiral. You're looking at that wedge. Or there's no wedge or dash to show because we don't have an sp3 atom. So we can't use that as our deciding factor. What we have to do is look at the structure we're drawing. Do we have a chiral atom? Yep, you need to worry about it. Okay? And then that's going to come down to how the reaction works. The double bond can react with our hydrogen in our first step either from above or from below. Okay? Which then means we form the carbocation. The chloride can react with the carbocation either from above or below. Both products come out. Question 4. Interestingly enough, question 4, we don't need to worry about chirality. The hydrogen reacts, okay, forming a secondary carbocation at this position. As soon as you have a secondary carbocation, what should you evaluate? Rearrangements. You get a hydride shift, and you put the chlorine at the more substituted position. Okay, no need for wedges or dashes. Okay, when we get to 5, we already drew out the answer. Okay, and hopefully, was everybody able to get the answer for 5?
Yeah.
Is that yeah? Okay, good. So you were able to break down and notice that we had hydrogens. Those hydrogens can react to the double bond, put on first, and then the OH can go through and react. Okay, there's a couple issues with that. That assumes that water is acidic. Is water acidic?
No.
No. Okay. Well, maybe water doesn't need to be acidic. What was the reagent used in steps 1 through 4? Strong acids. To get the alkene to react, what do you need to react it with? A strong acid. This reaction runs horribly. Mixing water with an alkene does not typically produce the alcohol. at least not in a very efficient yield, because water is not acidic enough to react with the alkene. So how can we facilitate that reaction to actually convert to the alcohol? Add a strong acid. Okay. That strong acid will supply the H+, which will then react with the double bond, and we now have the cation. Water can come in and attack. The issue is deciding what acid to add. Okay. We could add HBr. What's the issue with HBr? Bromide's a good nucleophile. We're now going to have a competition between the bromide and the water to do the substitute or do the final addition step. Okay? So the acid that we should choose would be sulfuric acid, because sulfuric acid provides a non-nucleophilic conjugate base. Okay? The other common one that you see in place of sulfuric acid would be phosphoric acid. Okay? Why use phosphoric acid instead of sulfuric acid? There it is, yeah. It's not as strong. Sulfuric acid is such a strong acid, it burns through everything. You add it to your organic material, it will start destroying it. Okay? We did a lab with sulfuric acid, and what was the end result at the end of that reaction, for those of you that were doing it in lab? A pot of black, tarry, nasty mess. Why? Sulfuric acid just started eating the crap out of our organic material. Okay? So if we want the reaction to go, we do need a strong acid. Sulfuric is a good strong acid, but if it's in too high of a concentration, it destroys material. So we can supplement with phosphoric acid. A little bit of a milder acid still allows for the reaction to occur. Okay? So it's a nice trade-off. Both phosphoric and sulfuric have the same general principle. The conjugate base non-nucleophilic due to resonance. Okay. If you look at the conjugate base of both sulfate and phosphate, both of them have massive amounts of resonance. Okay. Makes them exceptionally stable on their own. Okay. So, stereochemical traps, things that we have to watch out for. You think about where the attack comes from. Okay. When we're looking at our double bond reacting, we can have the electrons either come out to react with our hydrogen from above or from below. Okay. The other thing that I meant to go through and fix on this is that once we've gone through and reacted it, okay, we now have two positions where the hydrogen could go. Okay, where do we want the hydrogen to go? Which position? The position that allows for the most stable carbocation intermediate. Okay. How do we evaluate stability? Charge. Size. Electronegativity, resonance, induction. When looking at our, and officially hybridization, our tertiary, secondary, primary rules, and deciding that our tertiary was the most stable, which rule were we looking at? Induction. All the way at the bottom of the list. So this is a common thing that students will miss, is you'll think back to your substitution reactions, and in our substitution reactions, we typically looked at primary, secondary, tertiary substrates, and we kept them relatively simple. Okay? So we could look at those and say, oh, tertiary reacts in SN1. That when we then shift to a reaction that generates a primary carbocation, we immediately say, oh, that can't happen. But what if that primary carbocation has resonance? That makes it more stable, it stabilizes it. Okay? So try to avoid just tertiary always reacts and primary doesn't. Okay? It comes down to the stability. It's back to those 5 or 6 rules, depending on how you want to count them out. Okay? This is where you were thinking about, Corey. Our alkenes are achiral. If it starts achiral, then our product mixture must be achiral, which means when we go to our intermediate, okay, we have an achiral center here, okay, which then means our nucleophile can come in from either the top or the bottom, generating 2 products. Those 2 products make our product as a whole achiral. Each of the individuals is chiral, but both of them exist, okay, in equal concentrations. Okay? So we have to watch out for that. Okay? You may see this show up with wedges and dashes. Okay? You may also see it show up potentially with Hayworth projections, which, yeah, cool. So your textbook has a nice figure here starting with an alkene. Okay? They decided to go through and instead of adding hydrogen, they added heavy hydrogen, deuterium. Okay? Why would they do that? So that we can track it better through the reaction. We can see how that affects our chemistry. Okay? Remember, our double bond can react with that deuterium either from above or from below because it's symmetrical. Okay? No big deal on where it ends up going. Okay? So we see our deuterium being added from above or below. We have the carbocation. The carbocation can then be reacted with our nucleophile, our bromide, either from above or below, splitting us into two products in each of those two product situations. Okay? So when we're doing an alkene reaction, we have the potential for 4 products. The relationship between those 4 products is ultimately then what your questions start to ask about. Where are the arrangement of each of those new groups relative to each other? Okay. When we look at the acid-base reactions, we just get a complete smattering of possible products. That's why you end up with 4. When we move into chapter 12, we start to limit the number of products coming out of it because of the chemistry that's happening at each of those addition steps. Yes?
Would we also want to look at the likelihood of each product forming too? So based on cis-trans?
So we can evaluate our cis-trans setups if it comes into play. And in this case, it's not going to come into play because our deuterium, right, is small enough that it's not going to affect where the bromine comes in or the bromide comes in. Okay, so we should expect relatively equal concentrations of each of those 4 possible products.
So that was larger, say, like carbon?
If we made that deuterium, that first atom that was added, something bigger, is that going to change how the bromide's ability comes in to react with the carbocation? Yes. And that can potentially prevent one of those potential additions. Yes. So size still plays a role when we go through to look at our reaction. Kind of makes sense? Okay. The other nucleophile with a giant red O, what do you think we're referencing? Oxygen is a potentially good nucleophile. Okay, we could also look at nitrogen. I could have capitalized the N. So your halogens, oxygen, nitrogen, all of them are pretty good nucleophiles. Okay, so they all have the potential to go through and do the same type of chemistry. Okay, in our hydrohalogenation, hydro because we're adding hydrogen, halo, we're adding a halogen. In this case, we're doing a hydrobromination. Okay, in that reaction, we're adding hydrogen and bromine across the double bond. We've had everything coming out nice and neatly. Okay, one of the things that we can then think about is once we've made this product, what can it then do? Okay. If we look at the product of the hydrohalogenation, I have an alkyl halide. Alkyl halides have what chemistry available to them? Okay. All of our halogens act as good leaving groups, which then means our carbon becomes a good electrophile. Okay. That also means that the hydrogen at the beta position becomes partially acidic. Okay. So if we look at that functional group, we get the potential for substitution reactions. I can exchange the bromine for something else. We also get the potential for elimination reactions, okay, by removing that hydrogen. Okay. That's it. I'm not done. There's no other chemistry I can do there. Okay. Depending on what we are trying to do, I may want access to more chemistry. Maybe I want whatever that new atom is that I attach to the double bond to act as a nucleophile. Can bromine act as a nucleophile at this stage? No. Okay. So I can't build that structure necessarily any larger at the nucleophilic position or at our leaving group position. Okay. So maybe I want a different atom there, an atom that has the potential to hold more bonds, say like oxygen or nitrogen or potentially even carbon. Okay. So that's where we can come up with other nucleophiles. Okay. What other nucleophiles are there? Carbon's a tricky one. Oxygen. How could we get oxygen to come into this addition reaction? Okay. The oxygen would need to come in as a nucleophile, right? So we're saying OH, good idea, except now what's the problem? What does our addition reaction or reagent act as? A base or a nucleophile. What happens when we bring in a negative oxygen? They repel each other. That reaction can't work. So I like the idea of getting that oxygen to act as a nucleophile, but first I have to prime that alkene to allow it to react as an electrophile. The only way I have to prime it right now is to add a hydrogen to it. Okay? The hydrogen source is going to have to be added as an acid. Can I add hydroxide and an acid in the same system? No. Okay, I can't. Okay? Because the acid is positive, the hydroxide is negative. What happens when I put them into solution? They react with each other, and I don't get the reaction with the alkene. Okay? So now the hope is, how can I potentially go through and do this? I know I have to do an acid first. Okay? If I tried to go through and follow this up as a two-step reaction and add hydroxide, the hydroxide reacts with the acid, neutralizes it, we now no longer have the nucleophile. So I'm going to add it all at once. Okay, I could add it as H3O+. We'll take a moment to step away from that. We can add it as H2O. I still have a nucleophilic oxygen. It's not very nucleophilic, though. I've weakened its nucleophilic character. Do I necessarily care? It's the strength of my electrophile at this point. My electrophile should actually be really, really good, because what happened? What did our alkene do? Is a positively charged carbon highly reactive? Yep, I have a really good electrophile. I don't need to add a stupidly strong nucleophile. I can get away with a weak one, okay? Because my electrophile is so much more reactive. Okay? So how can I go through and present the reagents for that? Okay? Troy just suggested one thing. H plus and H2O make H3O plus. We could say H3O plus for this reaction. That becomes a bit questionable because we can't just make H3O plus. It's a charged molecule. It doesn't just exist. Okay? So we have to make it in situ. How can we make it in situ? Being in the container. Add an acid. We could add HBr. HBr will react with the water to get me H3O plus and bromide. I don't want bromide. Okay, so what can I do? H2SO4. Again, H3O won't work because that's a charged species. We can't add a charged species in a reaction. Okay? Kind of makes sense? Okay, what happens if we try to change this and say, now I want to get it to be a nitrogen? What do you think about the H2SO4? Is that something I'm still going to need?
No.
Why not? Okay, so you're saying we're getting rid of that, so let's get rid of that. What do we need to be reacting this with? Okay, NH3. Okay, so we didn't make the same mistake we made with the hydroxide. We made it a weak nucleophile, good, at NH3. Okay, now what do we do? Is our alkene ready to react with NH3? No, that's two negatives. Doesn't work. We need to polarize the alkene. How can we polarize the alkene? React it with an acid. Okay, so we add H+. Okay. We now run into a big issue. NH3, while being a nucleophile, is an even better base. If it is a better base than our alkene, what's our very first reaction? What's the very first product we get? NH4 with what charge? Positive. And then we'd have the alkene. Can I do my addition reaction? No. For those of you saying, well, but now we have a positive nitrogen, you're right. The nitrogen is positive, and that is something that you can then red flag as being a potential electrophile. But you have to be careful about it. For the nitrogen to act as an electrophile, what must happen? It must accept more electrons from our alkene, which then means it exceeds the octet. We have to break a bond. Okay? Which bond is best to break? The alkene is the best bond to break. That's being attached to the most electronegative atom, so we're looking at sp2 carbon. Those electrons come right back to the alkene. We cannot kick off one of the hydrogens, because then we'd have, careful, we would have, it would take the electrons and it would become hydride, H minus. So not an acid, because an acid is H plus. What can you tell me about hydride? Is that particularly stable? Is it charged? Yes, so that's already a bad thing. How about size? It is the smallest possible atom we have. Okay? Can an exceptionally small atom stabilize a negative charge? No. Okay? So already 2 ticks right out of the gate, bad. Next thing was electronegativity. Hydrogen is one of the least electronegative elements that we have access to. Yet another tick saying that's a bad idea. Resonance? No resonance. An inductive effect? There's no inductive effect. Nothing about that structure says stable, which then means it doesn't happen. The result we get instead is the electrons go right back, and we end up seeing as our end result no reaction. Okay? So why did I not put a capital N there? Because it doesn't work well in the standard addition reaction. Okay? So we're looking at all of those as potential options. We've got the reagents, what our goal was in mind. With sulfuric acid and water, great, it works. With sulfuric acid and ammonia, that would be our target, but what ends up happening instead? Okay? And this is where questions can get dicey. Sometimes you'll see no reaction. The other option you'll see, ammonium, and you're starting alkene, which I drew in the wrong spot. Okay? So it's not technically a no reaction because something did happen. Okay? So depending on the level of the question being asked, you may see either answer. Yes?
Could you control the formation of the product by taking some out until you have a hydrogen to react with the alkene?
Your carbocation structure is already acidic because it's super reactive. So it's dying to get rid of that hydrogen or have something come in and share electrons with it. Okay, which is easier to have happen? Pull a hydrogen off on the outside or react with the carbon on the inside? Pull a hydrogen. So as soon as we try to separate this into 2 steps, okay, form our carbocation with our sulfuric acid, we try to add the ammonia comes in, pulls the hydrogen right back off and takes us back to our alkene. So we end up not seeing that as a favorable reaction. Okay? So there's our big long acid catalyzed. Let's look at the question at the bottom of this. Does oxygen have to come from water? How else could I get oxygen into this reaction? How about that? Is that an oxygen? Yeah, would that work in this reaction? Theoretically, let's check. So let's go through to where it comes into play. Okay. Our important role is this middle step right here. That's where we should start off. So instead of it being H2O, it'll be OCH3. CH3, right? Still has lone pair electrons. Share those electrons up. We end up forming as a product. With a positive charge on that oxygen, right? Is that structure stable? No. What's the issue with it? It's charged. Okay. What can happen to stabilize that oxygen? It could try and break a bond. Okay. By breaking the bond, we're taking the electrons away from one of the atoms attached to it. Okay. Which means we have 3 potential atoms that we could pull electrons from. If we pull them from one of the methyl groups, what do we have? A zero-ary carbocation. Is that a good idea? No. So the methyl groups don't work. Let's pull it from that one. And we get a secondary carbocation, which happened to be the reverse. Okay? So using this as a nucleophile, sure, it works. We form an incredibly reactive structure that then says, screw this, and goes backwards. Okay? It's perfectly valid, sure. Why not? It can do it. But does it advance us anywhere? No. Why does water work? Water, being relatively simple with a bond to hydrogen, can ditch H plus to our solution. And we end up doing an irreversible acid-base reaction that gets us to our final product. Okay? So if we go back to our methanol, or sorry, not to give away answers or anything, our dimethyl ether, that won't work. We need this last step. I have to have a hydrogen attached to that oxygen so that I can initiate my irreversible acid-base step to allow this reaction to occur. Which means, what do I need to change about my alcohol? Or, Rick, about my ether. Needs to be an alcohol. Now when it goes through and does the reaction, what happens? Whoa, that was a really big eraser. Now I still have that hydrogen that I can remove and end up with my final product. My final product will end up being almost, other way this time. What happens? I'd have the oxygen attached to the methyl group, and my structure is now, oh, that hurt. I heard 3 functional groups shouted out, and all 3 were wrong. Ether. Ether. It's an ether. Okay? It is an unsymmetric ether, but it is an ether nonetheless. Okay? So it does not have to come from water. Okay? Our alcohols end up being good oxygen nucleophiles as well. Okay? We really need that last acidic hydrogen. As long as we've got that, we're pretty much good to run with those. Okay? Make sense? Oop. Okay. How about the other base? So we looked at the other nucleophile somehow in our reaction. What's our other base? Well, what was acting as a base in this reaction so far? The alkene. What do you mean other base? What's other than an alkene? What is reacting in the alkene? The pi bond. Is there another structure that has reactive pi bonds, say between 2 carbons? Like maybe the alkyne. The alkyne will go through and do similar chemistry. Okay? Same general idea. We can have the pi bond react with the hydrogen to form our carbocation. The bromine can come in and react. Okay? We now have an alkene. What could the alkene potentially do? It could react again, and we could push this all the way out to now having done 2 substitution or 2 addition reactions, and we would have 2 bromines attached to our structure. Where would we place those bromines? There's 2 options. On opposite sides, putting the bromine over here, call it blue or purple. The blue position is still the more substituted, which means it's still going to be the more stable carbocation. We end up putting the bromine at the blue position. And we end up forming what is known as a geminal dihalide. Okay, I think I've got that right. So you might see that term pop up. It's usually pretty rare. Okay, what's happening in our giant box? We could go through and look at the mechanism. Okay. We form our alkene, and then we could go through and process our way out. I do have a couple issues here. Okay. We do form the more stable carbocation. Why is it more stable? That's the two answers that we could come to, resonance and potentially secondary. Is it resonance stabilized? No, we're in orthogonal orbitals. The carbocation is not parallel to the pi system, which means the electrons cannot share between those two. We do not have resonance to stabilize that carbocation. Okay. Think back to our substitution reactions. What type of starting material or substrate did we say never reacted? Our vinylic halides never reacted, and the reason we said why? We can't form a carbocation on that carbon. Okay? That carbon is too electronegative. What does that suggest about the formation of that carbocation? Not going to happen. Okay? This is not an easy reaction to go through and do. Okay? We have to force it. High pressures, high acidity, and time to get this reaction to work. Okay? Because we end up forming a very, very unstable intermediate. Okay? So if we can push it hard enough, we could potentially go through and form this. Okay? So we give it a bunch of time and excess HBr, we can go through and we can overcome the result. Did I call it geminal? I did, didn't I? Hell yeah. Look at your money being spent on someone that knows what geminal means. Okay? We can force it to the geminal dihalide. Okay? Only if we have excess HBr and time.
How much time?
Okay? I think you're looking on the order of a day.
Really?
Yeah.
Is it not an issue that two big bromines are like right next to each other?
Which is another issue with this. Okay? That's why you need time. Your cation, once it's formed, is so unstable that it will end up reacting. Okay? So it's not a synthetically useful mechanism. Could you theoretically be asked this? Yes. What you need to remember, geminal dihalide. The halogens go to the same position. Okay?
Would that molecule be straight?
It would not be straight. Well, which molecule are you talking about? Right or left? Left is straight, right is not.
Okay.
Okay, this is linear. And this is, if we look at that center atom, tetrahedral. Paying someone that even knows how to spell tetrahedral. This is a great day. Okay. So, we've also used sulfuric acid and water as a nucleophile. What happens when it goes through and reacts? Okay? So we just said HBr, hard reaction, not very likely to happen. Okay? So let's push it though. Let's just do it. Push it all the way. What do you expect as a product? Okay, I heard someone suggest it. Want to shout it out again? I can turn it into another quiz. Okay, so work with me. Okay, geminal alcohols. It's the same general idea. We add the hydrogen, okay, to generate the more stable carbocation. We've got our water. The water can then come in, act as a nucleophile, react, and we end up with the geminal alcohol. Okay, that might be what we would expect out of this, and it turns out we don't even come close to that. What we get instead what? How'd that happen?
So my head first jumped over to the when the water comes in and attaches to the carbocation, the hydrogen that gets kicked off then reacts with the pi bond. That's what popped in my head first.
So there's our carbocation, first step. Then what?
Then the water comes in, reacts with the positive charge, and then you lose a hydrogen to form OH, and that hydrogen that gets lost goes in and reacts with the pi bond.
To the hydrogen, to that carbon.
Oops. No, you were still saying OH there.
Yeah, there's still an OH there.
If it reacts with the pi bond, it's reacting as H+. The pi bond has to react. We have to form the more stable carbocation. There it is.
So I wasn't taking into account the hydrogen that attached to the primary carbon on the first step you wrote. That's what.
Oh, that's what you lost. Yeah.
That's what I was missing.
Okay. Either way, any of that, all of that looks great to getting towards this point, because then we could have water attack again, right? Where the hell did that come from?
Ditch the other hydrogen, block the electrons down.
What is special about this carbocation? Stabilized via resonance. Does the oxygen want to be positive? No, so it can take the electrons from our hydrogen and we end up with our product. Okay? We're going through the same general ideas as that we went through with all of our addition reactions so far. We react with the acid, a nucleophile comes in, we try and stabilize, we continue the reaction along. The issue is that in that next step, we form a resonance stabilized carbocation. Okay. That's one of the things that can drive that reaction forward. That resonance stabilized carbocation is no longer sensitive to our acid-base reaction, and we're not going to get a second addition. Okay. To do some subtle erasing here, what is the relationship between those two structures? It's actually another name given to them. From chapter 5, I believe. One of those is known as the ketone, and the other one is what? An alkene and an alcohol. An enol. We have the keto-enol tautomerization. Remember in chapter 5, that real quick thing at the end, I was like, we'll kind of see it at the tail end of the semester. This is it. Okay. It also explains good, probably 50% of second semester OChem. Comes back to the same kind of relationship, the keto-enol tautomerization. They're known as tautomers because it's special chemistry, so we gave it a new name. Okay? So just be kind of aware of that. Questions? Okay, there's our keto-enol straight. Oh, I said chapter 7. It's not chapter 7. Maybe it is. It's one of those chapters. Earlier, we talked about it. Okay. It is our keto-enol tautomerization. We talked about it in comparison to looking at acids and bases. So it might have been chapter 6. Okay? Kind of makes sense? Unfortunately, it doesn't have to. You just have to know it. Okay. Your textbook has a pretty nice chart showing everything. The only thing I want to call out, actually this one is kind of cheating. You'll notice they're calling that carbocation resonance stabilized. Last time we looked at a mechanism here, we said that that cation was not resonance stabilized. Why is this one now resonance stabilized? Because of the benzene ring, okay? You have to be cognizant of when they're referencing different types of stability, what things are being used to stabilize. That cation is resonance stabilized because of the ring, not because of the double bond where the alkene or where our cation is located. Okay, kind of makes sense? Okay. Okay, what if we have more than one pi bond? Where should our H plus add? Could always turn this into another quiz. Work together, come up with it. Okay, let's say this half of the classroom, do question number 1, first one. Okay, right down the middle. Anybody on that side does the left question. Anything on this side does the right question. Figure it out. You can talk to the people around you, see what you can come up with. And I will draw your attention to this. I am calling out a clue here by saying where should the H plus add, though officially what you should do is react each of these with HBr. And predict the product. The very first question you should ask yourself is where should you put the H plus? That will determine what the rest of your reaction does. So we look at the left one. We got 2 double bonds to react. Okay? And one thing I didn't add in here is we're assuming 1 equivalent of HBr. Okay? So you can only react 1 double bond, okay? Which I think everybody had. Okay? Which double bond should we react? Well, are they different, number 1? Yes. Okay, well, we now have to make a decision. Which double bond should we react? Okay. We might say the terminal, because the terminal is our more reactive starting material, okay, because it's the end of the structure. But by reacting the terminal one, what would we end up with? We'd have to look at the intermediates formed, and we'd end up forming a secondary carbocation. Okay, secondary, that's allowed to happen. Okay, why did we not put it on the primary position? That's even less stable than the secondary. So at least when we react that rightmost double bond, our red double bond, we should end up with the secondary carbocation. That means the bromine would then go there. But what happens if we reacted the other double bond? We end up with a tertiary carbocation. Okay. Which one of those 2 intermediates is more stable? The tertiary, which means which one is more likely to form? The tertiary. And the result ends up coming out as the tertiary reacting, and we'd put our bromine there. Whoops, I've lost the double bond. Okay?
And there's no dashed or wedged, right? Because there's no carbons.
We don't need to worry about dashes and wedges here for a couple reasons. Number 1, I don't want to worry about it right now. And number 2, that's not a stereo center, so we don't have to worry about it here. For the next product, we also won't worry about it when we look at it, even though we do end up with.
Okay.
Yeah. Okay? Does that first one make sense? We're all on the same page?
Would steric hindrance play a role in that bromine attacking?
That steric hindrance would absolutely play a role in the bromine attacking that tertiary position. You're right, that step may slow down. Do I care about that step?
No.
Okay, I don't care about that step because
This is the rate.
our rate determining step was the formation of the carbocation. So I don't care that that next step may have some issues with it. It's not the slow step. My first step is the slow step. That's where my focus stays. Okay? What about the next one? Okay, the double bonds are the same. So does it matter which double bond we pick? No. Okay. Which double bond do you want to pick?
That one.
The right one. Okay. Way to pick the one that I wasn't going to go for, but that's fine. Okay, we can go through and we pick the right one. We'd have our carbocation at the secondary position. This is actually not just a secondary position. This is resonance stabilized. Okay, whenever we're going through and looking at a mechanism, we should be proving why an individual step is a valid step. And one of those things is saying, hey, there's resonance. Check it out. So let's check it out. What happens when I do that resonance? I put the positive charge at the primary position. Okay, and now what would happen?
Sorry.
Now what happens? The bromine can come in and react, and I end up with 2 possible products. And I think I put too many carbons in that. Did you really just say good job? Ah! Fix it finally?
Yeah.
Yeah, that's right.
Which of those products was formed?
The first one.
The second one.
So first one, why the first one?
Because the carbocations on the secondary.
Secondary carbocation. Why are you saying the second one?
I was thinking terminal alkene in the product.
Look at the double bond. In the first one, we have a terminal double bond versus the second one, internal. What does that mean?
It's more stable.
The internal is a more stable product, which means that one drops in energy. So we would suggest, if we look at the products, that we have the second one being our product. Yet, if we look at the intermediate, it's the first one being the product. What does this mean? Both. Depending on the conditions that we run the reaction in, both are potential products. One of those products is known as the thermodynamic product. The other one is known as the kinetic product. How do we decide? You need to go through and look at an energy diagram evaluating your full mechanism and apply that out and see how it stacks. So if we start this off, our reactant in both cases is the same. We'll start somewhere in the middle as far as our energy goes, and then we'll move our way through. We'll call this our red product for our top. We'll call it our blue product for the bottom. Okay. What do you want to look at first, intermediate or product? Intermediate. So let's add our intermediates now to our energy diagram. Which one is higher in energy? Which one's lower in energy? Blue is higher because primary. The red is lower because it is secondary. We could go through and even add our little humps on top of those. Based on that information, which one would we expect to form? Red because lower in energy. Now let's move to our products. Which of our products? Is there a difference in energy between our products? Yes. Okay. That does become more difficult to evaluate because they're neutral, so it becomes harder to find the reactivity. Okay. But at least one of you was able to zero in on the most reactive thing on that structure. The most reactive thing is the pi bond. So now you have to compare the pi bond between those structures and say, is it the same reactivity? The terminal is more reactive, which makes it higher in energy. Okay. This should still be higher or lower in energy than our reactant. It should be lower in energy than our reactant because one less pi bond. Look at our blue structure with a terminal internal double bond. I see it. It should be located lower in energy than our red one. If we go through and connect out our lines, we end up seeing our lines cross over in the formation of our product. What's your question? So deciding on when is this important comes down to the exact energy values between those. In some cases, it's significant enough that we don't see a difference. We only end up with one product. Okay? Other cases, they're close enough that we do see a balance between those, and it depends on the reaction. When looking at the addition reaction, they are close enough that our conditions largely determine which product we get. Okay? So how can we alter these conditions then to adjust which product we get? Temperature. Okay. Which product is going to form first, red or blue? Red. It will always form first because lower activation energy for our slowest step. Okay. What is going to allow me to get the thermodynamic product? Well, I have to get all of my kinetic product and turn it back into the reactant. How can I get it to turn back into the reactant? I need to reverse the reaction. But to reverse the reaction, I have a large activation barrier. So what do I need to get that, clear that activation barrier? Energy in the form of heat. If I add enough heat, I can cause my kinetic product to reverse reactions to go back to the reactant. I am still going to see a favoring for the kinetic product. Okay? But 1 out of 10 times, I make it up to my thermodynamic higher energy state. What then happens? It can drop down to the lower energy state of our thermodynamic product, and now what happens? That won't ever go back. The blue one ends up being irreversible. Because it is irreversible, I cannot then reverse it, sorry, okay, to get us back to our kinetic product. So when we look at a reaction trying to decide is it reversible or irreversible, okay, we've done this before. If I take a look at, let's say, this species, is this reaction reversible or irreversible? Okay, two approaches. First approach, look at your pKa's. pKa for the carboxylic acid, because you've now spent the time to memorize those. 4. pKa for water. 15.7. For those of you with bad memories, you can memorize it as 16. What does that say? The products are favored. By how much? A lot. Remember, this is a logarithmic scale. You're looking at, what is it, 1200? I don't know how to compute logarithms. Anybody in higher levels of calculus can probably do that. And can tell me what that exact difference is, but we're looking at a lot of zeros, okay, favoring the product, which then means irreversible. What happens if we change this structure around to, those of you in the lab should love this example. Whoops. Shoot, I can't pick that one. Sorry. Those of you not in the lab, don't worry, because I can't pick that example. Whoops, that 16 was still fine. What if we go through and do this reaction now? What's the pKa of our alcohol? Hint, it's already up there. 16. Okay, what does that mean? It's reversible. Okay. How else could we do this if I didn't have the pKa's? Coming back to our energy diagram, what is the most reactive thing on the left-hand side of the equation? OH minus. What is the most reactive thing on the right-hand side of the equation? O minus. Okay, are they charged? Yep, no difference. Size? Same size. Electronegativity? Resonance? Inductive effect? What does that mean? The stability of each of those species are roughly the same, meaning the reaction is reversible. If we switched it to the one we started with, between carbon and hydrogen, there is technically a difference. It is not enough of a difference to do much of anything. Now what happens? Charge. Size. Electronegativity. Resonance. Significant difference in resonance, meaning this structure becomes more stable. If this one's lower in energy, our reaction just became irreversible. Okay? You can use pKa's. You can also evaluate charges and stability. Those same 5 stupid rules that you need to have memorized because it applies to every single reaction without a doubt. Okay? Back to our conditions. How can I favor the thermodynamic product? Add heat. How can I favor the kinetic product? Don't add heat. Also known as cold and hot. Okay. That can help us balance between those two products. Okay. Can conjugated alkenes react in other fashions? Yes. That's the tricky reaction dealing with Diels-Alder. I will post a specific announcement linking out to the Diels-Alder video. There is a lecture slide already posted online. Okay. It is also in the lecture video links already, if you've seen that. Okay. I set it for like week 15. You can watch that and see what's going on with it. I do not blame you if you start to look at the Diels-Alder video and you're like, holy crap, do I really need to know this? No, you don't need to know it. Okay, we'll talk about it in second semester. Though officially it's part of our curriculum. So there's your warning. I've given it to you. You have access to it. You are officially responsible for learning it this semester. That's the way it goes. Okay? So, questions about our conjugated alkenes. Was it your hand? Somebody had a hand.
It was my hand. I was thinking, well, if you wanted to reverse that reaction, could you then just take the root of product y and something else in?
So we can change how much we're making by doing kind of Le Chatelier balancing on that, trying to shift it. The other way to really make it reversible, change the reagents you're using. That's the biggest change that you can make. Okay? In first semester, the reagents are most negative species are typically oxygens and nitrogens, both of which can stabilize a negative charge fairly well. What if it had been H minus? Now reversibility isn't even a question. Okay? There's no way that reaction is going to reverse because can H minus stabilize a negative charge? No, not even remotely. Take it a step further, going back to Le Chatelier, one of our products is hydrogen and gas. To reverse the reaction, the hydrogen gas must react with this. What does a gas tend to do? Float away. If it's not even present as a reagent, can we reverse the reaction? No. Okay. So multiple things come back to evaluating what you learned in 152, and that's kind of the build-in to second semester organic. Looking at reversibility, how does that reversibility affect the different products we get out of it? This is your kind of fun intro into second semester. Okay. It is also where we will end chapter 11 and pick up chapter 12. Okay. Questions about it? Troy? No? Okay. Really stupidly quickly, isoprene happens to be a super, super common alkene found in nature. Okay? Steroids, cholesterol, all of that. How do you make those? Isoprenes. That's it. Okay. It's the basic skeleton structure. Do you guys have a different question? No, we'll just assume not. Addition reactions, chapter 12. Okay. In chapter 11, our positive atom was H. Chapter 12, our positive atom is not H. Okay. Some of those are obvious electrophiles, some of them are less obvious. Okay. In almost all of the examples coming out of chapter 12, they're almost always done in two steps. Okay. We react it first with the electrophile, then we react it with the nucleophile. Okay. So this section here is a bit misleading. Okay. Because they're done in two separate reactions. So, mechanisms of our addition. How does it work? The electrons from our pi bond need to react with what? A positive species. Okay, hydrogen was chapter 11. We're no longer in chapter 11. We're looking at a positive species. How do we decide which is positive, X or Y? It's arbitrary at this stage because... no. How can we decide which one is positive and which one is negative?
Just say which one's positive.
Which one's positive, which one's negative?
We don't want yours to.
Boron is positive, not the H. The H actually is negative. How on earth would we figure that out? Oh, that's an interesting question. Let's try another one. Mercury is positive. How do we decide that? There it is. We decide our atoms being positive or negative based off of electronegativity. Okay, so let's add some information here. Let's say, I'm sorry, not really. X is less electronegative than Y. What does that mean? Okay, X should be positive because it was less electronegative. That gets us our partial negatives and partial positives. We can then apply that same logic down to our alkene. Which of our carbons is more positive or negative?
The one with 2 R groups is more negative.
The one with 2 R groups is more positive because we have more electron density there. The other one is more negative. What does that mean? The electrons from our pi bond, stupid pen, will come out and react with our positive species, our X, okay, to produce, no alkene. An X, we've got an R, what do I have, double prime, and an R prime, and an H. What is the issue that's going to potentially arise with that? Stereochemistry. So if we go through and say this one's wedged, that one's dashed, this one would have to be wedged, that one's dashed. Okay. That would assume we formed a carbocation, which would mean a positive charge there, and our Y could come in either from the top or from the bottom. Okay, plus the potential enantiomer in it, because our X could have come in from the bottom. Okay. What if, in the course of this reaction, those were added at the exact same instant? Where would I place Y? If X and Y are added to the double bond at the exact same instant, can the Y come in from the opposite side? No. It must be added from the same side, and I could end up with the Y located there. What if, somehow or another, this was added in a 2-step process where the X somehow prevents the carbocation from forming? Where would the Y then potentially add? On the other side, because the X is now protecting the top side, and we'd end up with Y being on the opposite end. Anybody getting an idea about how this problem can become much more difficult? We've added a lot more specificity to the reaction by being a little bit more selective about our positives and negatives. Okay. That specificity results in a reduced number of possible products. Okay. It also sets us up with a situation where we can now look at how the addition occurred, our X and our Y, and in one case we can refer to them being added on opposite sides versus the same side. These pick up very characteristic names. If they were added to the same side, we might say that they were cis, but that assumes there's a double bond. Is there a double bond? No, so we can't say cis, we'll call it syn addition. It's a description of the verb. And the other one we have trans, but there's no double bond. Where are X and Y relative to each other? Anti-addition. For those of you saying, why can't we call them cis and trans are adjectives. Anti and syn are adverbs. They're operating on a different article of English language. That's why they're different names. Just so you're aware, when talking about it, you'll be able to clearly explain either way. It won't be an issue. On a test, you have to be a little bit more careful about syn and anti. Okay? So we will pick up there.